In the presentation on parametric surfaces, I had promised you some repetition, and that is going to happen now because basically we're going to revisit the parameterizations of spheres and of cylinders, this time used as a way to coordinatize three-dimensional space. And so we're talking about non-rectangular coordinate systems here. In particular, we will talk about cylindrical and spherical coordinates. Let's take a look at the why and the how. So, basically, the biggest technical problem in multivariable calculus is the number of variables. Well, duh, right? I mean, that's not that hard to see, but basically, even though that's not a terribly deep insight, it shows that things should get simpler if we just reduce the number of variables. So, for example, if you look at the function e of rho being 1 over 4 pi epsilon times 1 over rho, and if you have had electrodynamics already or are about to take it, this is the electric potential around a point charge that is scaled to size 1 at a distance rho away from the charge. Well, that function is certainly easier to read than the function e of x, y, z being 1 over 4 pi epsilon 0 times 1 over square root x squared plus y squared plus z squared. Even though, as soon as we set rho equal to this square root, they are the same thing and they would describe the same phenomenon. And so, of course, we cannot simply take any combination of the variables x, y, and z and hope that things get simpler. But rho equals square root x squared plus y squared plus z squared is not a random quantity. It is the distance from the origin in 3 dimensions. So basically, if I had the choice to represent the electric potential of a charge that is scaled to size 1, which technically is a really huge charge, in this form with a rho or in this form with x, y, z, I would certainly choose the rho, and that is also how it is reported in physics texts, except that the rho is often called r, and that's just notational difference between disciplines. Well, we will discuss two coordinate systems that allow to simplify things a little bit, and both of them rely on a distance measurement. Cylindrical coordinates will be based on a distance from the z-axis, and spherical coordinates are based on the distance from the origin. And we will start with cylindrical coordinates, which should be familiar because they're nothing else but polar coordinates with an additional z-coordinate. So if you understand polar coordinates, then cylindrical coordinates should not be a problem at all. So let's review polar coordinates real quick. What was the idea? Well, we've got our usual xy coordinate system, and if we're looking at a point in that coordinate system, we know we could work with the projections and get the x and y coordinates, but we could also measure the distance from that point to the origin, which is r equals square root x squared plus y squared, because the sides of this right triangle have length y in the vertical and x in the horizontal. And we could look at the bearing, and that in mathematics is measured off the x-axis, so this angle theta of the x-axis. And basically then, as soon as we know that, okay, suppose we're standing at the origin, if we know where to look, which is what the theta gives us, and how far to go, we know where the point is. And that then corresponds to, of course, also to the rectangular coordinates, where y is r sine theta, because, well, theta, sine theta is y over r, and x is r cosine theta, because cosine theta is x over r. Okay, so, and then basically the rectangular way of representing that point is equivalent to the polar way of representing that point, as long as we make sure we interpret the numbers correctly. Alright, so this is used in navigation on the surface of the Earth. This is not quite how ships navigate, because they're looking at bearings off a due north, but this is certainly how ocean-going vessels have been navigating for a while. They look at what bearing they have to go, and they look at how far they have to go. If we now consider objects that are not constrained to the surface of the Earth, well, we could do the same thing, right? We get ourselves our xyz right-handed coordinate system. We look at a point that is now in space. We can project that point down to a point in the xy plane. And, well, then we've got coordinates xy, but we also have a height z, most importantly. And this point down here is the point xy0, which, if we measure the distance of that point to the origin, can be expressed in terms of r being square root x squared plus y squared, and that angle theta that comes off the x-axis. And so that means polar coordinates, and then, okay, tangent theta is y over x, so that would be because this right triangle has opposite side y and adjacent side x, so tangent theta is y over x, and that means that the point with rectangular coordinates x, y, z is also representable in cylindrical coordinates r, theta, and z. The definition is that in cylindrical coordinates, the position of a point in three-dimensional space is described by coordinates r, theta, and z, where r and theta are basically the polar coordinates of the point's vertical projection onto the xy plane, and z is the rectangular z coordinate of the point. So if we're looking at that one more time, we take our right-handed coordinate system. Here's our point. We project the point down, and that gives us the height z first of all, so that's this z here. Then we look at the bottom point x, y, 0, and we express that in polar coordinates. So this r here is this r here, and then this angle theta here, that is this angle theta here. And again, in looking already ahead at the transformations, tangent theta is y over x. That's what we really want to remember for the transformation. And again, the point is equally well represented in cylindrical as well as rectangular coordinates. Note that the angle theta is sometimes called phi, and that happens especially in physics texts, so be careful whenever you are looking at a text that uses cylindrical as well as spherical coordinates, and make sure that you are aware of the conventions that the authors use. Okay, so now let's just keep this picture around and let's think about how we convert from rectangular coordinates to cylindrical coordinates. Well, if I have x, y, and z, well, then I get r from x and y as r equals square root x squared plus y squared, or if we don't want to carry around the square roots, as r squared equals x squared plus y squared. And for theta, I really just want to remember that tangent theta is y over x, because when I take the arctangent, I only get an angle between negative 90 degrees and 90 degrees, between negative pi halves and pi halves. I will only get an angle in the first or fourth quadrants, and then I have to look a little bit more as to how the sines of y and x align in order to determine whether theta has to be augmented because it's an angle in the second or third quadrant. We're going to see how to do that. And z, of course, is just z. That's the easiest transformation among the three. If we want to convert from cylindrical coordinates to rectangular coordinates, well, let's see. We would have that the x, well, let's see, cosine theta is x over r, and so that means x is r cosine theta. Sine theta is y over r, so y will be r sine theta, and z is z. So again, knowing the geometry or remembering polar coordinates basically does the trick in our conversion to and from cylindrical coordinates. And so yeah, here is also where I want to give the shout out to the parametrization, to parametric equations, because the standard parametrization for a cylinder is exactly that, right? X will be the radius times the cosine of the angle that goes around, y will be the radius times the sine, and z just tells us the vertical extent of the cylinder that we are parametrizing. That's also going to come back to us as we are looking at coordinate surfaces. Okay, as an example, well, find the rectangular coordinates of the point whose cylindrical coordinates are 5, 5 pi over 4, and negative 2. Well, we just have to remember the formulas, so it's just computation. X is r cosine theta, which will be 5 times cosine 5 pi over 4. Cosine 5 pi over 4 is negative 1/2 root 2, so this will be negative 5/2 root 2. Y is r sine theta, which is 5 sine 5 pi over 4. Sine 5 pi over 4 also is negative 1/2 root 2, so this is negative 5/2 root 2. Z is z, which means z is negative 2, and that means the rectangular coordinates are negative 5/2 root 2, negative 5/2 root 2, negative 2, and that's it. Now, doesn't that feel nice after all the more complicated stuff that we're doing? This is downright relaxing, right? We just work with formulas that we're familiar with and plug things in, and that's almost the hardest thing we're going to do in this presentation, because we're going to work a little bit with pattern recognition, but it's really nothing terribly much worth worrying about. So, what else can we do? Well, we can translate rectangular coordinates into cylindrical coordinates. Alright, so what do we have? We have r being the square root of x squared plus y squared. And with r being x squared, square root of x squared plus y squared, all we have to do is plug in the numbers, so we get square root of -1 squared plus root 3 squared, so that's square root of 4, which is 2. For theta, remember, we know tangent theta is y over x, and so that means that the tangent of theta is negative root 3. But now we've got two possibilities, and we have to be careful here. This angle, with x being negative and y being positive, this angle is in the second quadrant. And okay, so z is z, which is 4, and because theta is in the second quadrant, we have that theta is not just the arctangent of negative root 3, but it's actually the arctangent of negative root 3 plus pi, and that ends up being negative pi thirds plus pi, which is 2 pi thirds, and that also makes sense because if you visualize that angle, that is an angle that sticks out into the second quadrant. And that means that the cylindrical coordinates are 2, 2 pi over 3, and 4, and that's already the whole translation. Okay, the other thing that we can do once we've got these coordinate systems is we can also translate equations from one coordinate system to another, and that again can and does help because it may help us save variables. So for example, if I have the cylindrical equation 4x squared plus 4y squared plus z equals 6, and I want to convert that to cylindrical coordinates, what do I realize? Well, I could see right away that I've got an x squared plus y squared, or I could do the translation mechanically and just plug in x, y, and z. I chose here to plug in x equals rho cosine theta and y equals rho r sine theta, r cosine theta and r sine theta. And when I do that, well, I end up with 4r squared cosine squared theta plus 4r squared sine squared theta equals plus z equals 6, and I realize I can factor out the 4r squared, and cosine squared theta plus sine squared theta is equal to 1, so I end up with 4r squared plus z equals 6, and that means z equals 6 minus 4r squared. What is the advantage of that? Well, the advantage is if I have that z is equal to 6 minus 4r squared, that looks like a parabola that opens downwards, and because r is greater than 0, it's actually just the right half of a parabola. And then I know because there is no theta, it's symmetric in theta, which means it is cylindrically symmetric. So this graph is technically half a parabola rotated about the z-axis. So here is z equals 6 minus 4r squared as just a cross section, and then if I rotate that around in theta, I get exactly the picture that it should be, and that is it is this paraboloid, which is obtained from, here's just z equals 6 minus 4r squared set up in 2 dimensions, and then the absence of theta does the rest. So with good visualization skills, we can reduce the number of variables here, and that is certainly helpful as we are doing computations. Okay, well, when we come to spherical coordinates, basically the ball game changes, and we want to measure the position with quantities that are all available at the origin. So you could say cylindrical coordinates in some ways is navigation of airplanes off a tower, where you have a bearing and a ground distance, because you have all sorts of tracking systems that allow you a bird's eye view, and the airplane may even itself report its height. Well, now let's suppose that you have lost contact with the airplane. Then all of a sudden you need to measure all the quantities in order to determine where the airplane is with stuff that is available at the tower, and the tower would then be the origin. So how would you do that? Well, you give yourself an x, y, z coordinate system. You have a point here, and let's pretend that that's an airplane. Well, with radar pings and so on, you ought to be able to measure the line of sight distance between your location and this point, between the origin and the point, or between your location and the airplane. And that distance is rho, and in Cartesian coordinates, that distance is just the square root x squared plus y squared plus z squared from the origin. Sure. Then you ought to be able to also determine the bearing, because the bearing is just the angle theta of the z-axis, of the x-axis that we had before, because when you are sitting here at the origin, that's just the direction in which you look horizontally as you look towards the plane. So that angle theta ought to help, and well, then we just again remember that tangent theta is y over x, because that's how we make the connection between rectangular and spherical coordinates. And finally, well, you could also look at your angle of elevation for your line of sight, and it's actually customary in mathematics to measure the angle of the z-axis, and that's because, as we have seen in the presentation on planes, it's really hard to figure out an angle between a line and a plane. It's a whole lot easier to figure out an angle between the z-axis and another vector, and so that angle is called phi. And what do we know about the angle phi? Phi is the arc cosine of z over rho, and that is because if phi is the angle here, then phi is also the angle in this right triangle, and that means that the cosine of phi will be this z divided by rho, and that's going to help us as we derive formulas. Again, x, y, z in rectangular coordinates has an equivalent representation now, rho, theta, phi in spherical coordinates. And, well, that means now in spherical coordinates, the position of a point is described by rho, theta, and phi, where rho is the distance of the point from the origin, theta is the angle between the positive x-axis and the vertical projection of the position vector into the xy plane. So theta is the angle that we know from cylindrical coordinates, and it is also called the azimuthal angle. And phi is the angle between the positive z-axis and the position vector of the point, and that is also called the polar angle. And, well, here is the picture one more time, a right-handed coordinate system, x, y, z. Here is our point. Rho is the distance to the origin. If we project down and over, we get the azimuthal angle as the angle between the projection of the position vector into the xy plane and the x-axis, and tangent theta is y over x. And the polar angle is the angle of the z-axis, and that is the cosine inverse of z over rho. Representations are equivalent, and we should note here the Greek letters theta and phi for the angles are sometimes interchanged, and that again is especially the case in physics texts. And so again, when you read a text that uses spherical coordinates, make sure you understand the author, you are aware of the conventions of the author, whether theta and phi are as in this presentation, which is I think how it's typically done in calculus text, or if theta and phi are indeed reversed from our point of view. Of course, from the physicist's point of view, our setup is the reversed one. All right, well, so if we look at these spherical coordinates, and again, rho is the distance to the origin, theta is the angle of the x-axis, and phi is the angle of the z-axis. I keep clicking through that because I want you to really remind yourself over and over again what the angles are. Well, then if we convert from spherical coordinates to rectangular coordinates, well, x is rho cosine theta sine phi. How does that come about? Well, we do know that x is r cosine theta, right? So this is the r, but this r, if phi is here, then sine phi is this r divided by rho, and so that means that r is rho times sine phi, and so then r cosine theta will be rho sine phi cosine theta. Same thing's going to happen for y, because what happens for y? Y is over here, and we know that if we refer again to if we refer to cylindrical coordinates, then y, this distance here, is so that sine theta is y over r, and r still is, because phi is sitting here, sine phi is r over rho, which means r is rho times sine phi, and then r times sine theta will be y, so that will be y equals r being rho times sine phi times sine theta. And finally z, same story, phi is up here, z is here, so cosine phi is z divided by rho, and that means that z is rho cosine phi. And so the way to remember that conversion is that you basically have something that looks just like polar or spherical coordinates here. It's just that in x and y you multiply with sine phi both times, and in z you multiply rho with cosine phi, and that is definitely a set of equations that you ought to memorize. Notice that, again, shout out to the parametrizations for spheres. This is basically the parametrization of a sphere, where, as we had seen in the presentation on parametric equations, that theta makes sure we've got those circular cross sections going around, and phi makes sure that we reach all the cross sections, and we know that because theta has to go all the way around, theta has to go from 0 to 2 pi, but then for the coordinates as well as for parametrizing a sphere, we only need phi to come off the z-axis from 0 to pi, and that is because if we keep going, anything that we would pick up with phis that are bigger than pi have already been picked up with thetas between 0 and 2 pi. Okay, so we draw our picture. Right-handed coordinate system. Here's the point. Rho is the distance to the origin. Theta is the angle of the x-axis. Phi is the angle of the z-axis. And we've got these two representations. If we want to convert from rectangular coordinates to spherical coordinates, it's a little bit easier, because rho squared is x squared plus y squared plus z squared. That's what we already have. We just squared both sides to get rid of the square root. We know tangent theta is y over x, with the usual caution that we can't say more than that because the arctangent might not reach everything. And finally, cosine phi is z over rho, and that means actually that phi is arc cosine of z over rho, and that is because the arc cosine reaches everything between 0 and pi, which is what we need to reach for phi. Okay, as an example, if we convert the Cartesian coordinates 0, -2 root 3, -2 to spherical coordinates, how do we do that? Well, it's just computation. Just use the formula. Rho is square root of x squared plus y squared plus z squared, so that would be the square root of 0 plus 12 plus 4, right? And that's the square root of 16, which is 4. No problem there. Tangent theta is y over x, and that's kind of strange because we're dividing by 0. Well, when x is equal to 0, we are on the y-axis, and that's perfectly fine. Y is negative, so we're on the negative y-axis. The angle that corresponds to the negative y-axis is 3 pi over 2, because we have to go from the x-axis 3/4 of the way around to reach the negative y-axis. Okay, and then cosine theta is z over rho. Well, we've got z being -2, we've got rho being 4, so that will be -1/2. And that will mean that phi is the arc cosine of -1/2, which should be, that should be 5 pi over 6, is that right? Phi equals 2 pi over 3. Give me a second here. Yeah, that actually is correct. I had my wires crossed a little bit. Basically, -1/2 is reached pi over 6 past pi halves, and pi over 6 past pi halves is 2 pi over 3. So yes, phi is 2 pi over 3, and that means the spherical coordinates are 4, 3 pi over 2, 2 pi over 3, and that's it. Okay, simple but important observation. If you want to convert from cylindrical coordinates to spherical coordinates and vice versa, you just convert to rectangular coordinates as an intermediate step. And so, for example, if I want to convert the spherical coordinates 2 pi over 4, pi over 3 to cylindrical coordinates, yeah, okay, the pi over 4 is the same angle, but basically it's just computation, and we go through x, y, z first. So x is rho cosine theta sine phi, which would be 2 times cosine pi over 4 times sine pi over 3. Cosine pi over 4 is 1/2 root 2. Sine pi over 3 is 1/2. So 1/2 root 3, sorry, that's right, because the sine goes up. So that's 2 times 1/2 root 2 times 1/2 root 3. So that ends up being 1/2 root 6. X is rho sine theta sine phi. So that'll be 2 sine pi over 4 sine pi over 3. Well, sine pi over 4 is 1/2 root 2, the 2 stays, and sine pi over 3, as I just embarrassed myself, that is still 1/2 root 3, so that ends up being the same number as above, so that's 1/2 root 6 also. And z is rho cosine phi, and so the cosine of phi would be 2 times cosine pi over 3, and cosine pi over 3 now is 1/2, and so that means 2 times 1/2 gives us 1 here. So that gives us that x, y, z is 1/2 root 6, 1/2 root 6, and 2. That should be a 1. Okay, sorry about miscopying. That actually is supposed to be a 1, so it's 1/2 root 6, 1/2 root 6, and 1. That's what we keep with us, 1/2 root 6, 1/2 root 6, and 1. That means that r is square root x squared plus y squared, which is the square root of 1/2 root 6 squared plus 1/2 root 6 squared. let's see, that would be, if we square that, we get 6 over 4, which is 3/2. So it's the square root of 3/2 plus 3/2, which is the square root of 3. And tangent theta is y over x. Y over x is 1/2 root 6 over 1/2 root 6, which is 1. And because this is in the first quadrant, theta actually ends up being 45 degrees, or pi over 4. And z, of course, is still z, which is 1. And that's the whole conversion. Now, we can also convert equations from one coordinate system to another. So, for example, I can convert rho equals 4 cosine theta sine phi in spherical coordinates into an equation in Cartesian coordinates. And, well, again, just remember what spherical coordinates are. We've got rho being the distance to the origin, we've got theta being the angle of the x-axis, and we've got phi the angle of the z-axis. So, cosine theta, well, cosine theta is x over r, right? Because it is x over this radius r here, which would be x over square root x squared plus y squared. And so we're mixing things a little bit here. Sine phi, well, phi is over here. Sine phi would be this one over that one, so it would be r over rho. It would be square root x squared plus y squared over square root x squared plus y squared plus z squared. And so that would mean that rho equals 4 cosine theta sine phi is just, if we substitute it in, rho is here, cosine theta was x over square root x squared plus y squared, and sine phi was square root of x squared plus y squared over square root of x squared plus y squared plus z squared, and that is an equation that only involves Cartesian coordinates. Now we realize that this square root of x squared plus y squared cancels with this one, and we can multiply the square root x squared plus y squared plus z squared over. And so what we end up with is x squared plus y squared plus z squared equals 4x, which ought to be a sphere, and we can actually work that out, because if we bring the 4x over and complete the square, we get x squared minus 4x. The term that completes the square is a plus 4 minus 4, plus y squared plus z squared. And so that gives us, if we bring the negative 4 over, the y squared plus z squared stays. X squared minus 4x plus 4 is x minus 2 quantity squared, and that is the best way to write that Cartesian equation. And it is an equation of a sphere. The radius is 4, and the origin is at 2, 0, 0. Conversely, we can also take an equation 4x squared plus 4y squared plus 9z squared equals 1 in Cartesian coordinates and convert that into an equation in spherical coordinates. And if we do that, well, we could do pattern recognition and break things out. We could say this is 4x squared plus 4y squared plus 4z squared plus 5z squared, and end up with 4 rho squared plus 5z squared. Or we could just go ahead and substitute everything in and then practice our working with squares of sines and cosines a little bit, and that's what I chose to do here. So 4, that also reminds us x in spherical coordinates is rho cosine theta sine phi, right? That's something we've got to memorize. Y is rho sine theta sine phi, and z is rho cosine theta, and I've just plugged all these in. Right hand side is still 1. So now if we square all this stuff, we get 4 rho squared cosine squared theta sine squared phi, 4 rho squared sine squared theta sine squared phi, plus 9 rho squared cosine squared phi equals 1. And now we can factor a few things out, because the 4 rho squared is in common in the first two terms, and the sine squared phi is in common in the two terms, and what's left is just cosine squared theta plus sine squared theta, which is 1. So we get, and I've actually factored out a rho squared out of everything. Okay, so rho squared factored out of everything. 4 sine squared phi factored out of the first and the second leaves us with cosine squared theta plus sine squared theta here. Rho squared factored out of the third term leaves us with 9 cosine squared phi. Right side is still equal to 1. Cosine squared theta plus sine squared theta is 1. So this ends up being rho squared 4 sine squared phi, that is correct, and then the 9 cosine squared phi is 4 cosine squared phi plus 5 cosine squared phi. The right side is still equal to 1, and so that means this is rho squared plus times 4 plus 5 cosine squared phi, and that's it. That's about as condensed as it can be, and you can see this ellipsoid therefore can be expressed in spherical coordinates with two variables, rho and phi rather than with 3 variables, but that is hinging on the fact that we have 2 coordinates where it has a circular cross-section. Okay, we are closing out by discussing a little bit of symmetry and the coordinate surfaces. Basically, in any coordinate system, the objects that are obtained by keeping one variable constant and letting the other variables be arbitrary are called the coordinate lines if we're looking at 2-dimensional space, or the coordinate surfaces in 3-dimensional space. And basically these coordinate lines and coordinate surfaces tell you a little bit about what kinds of symmetries work well in that coordinate system. So coordinate lines and coordinate surfaces can be used to determine what kinds of shapes are most compatible with a given coordinate system, right? And any shape, of course, can be represented in any coordinate system if necessary with several pieces. Because, for example, we can represent a circle with 2 functions, y equals plus minus square root of 1 minus x squared, circle of radius 1 around the origin, right? But that's inconvenient. And so that's exactly the flip side of that coin. Some of those representations may not be very elegant, and we can think of the same thing, representing a circle with 2 functions, y equals plus minus square root 1 minus x squared. We're going to see more of that when we do integration, when we try to represent round objects in rectangular coordinates. That's not going to work too well, and that's where in 2 dimensions polar coordinates will help, and in 3 dimensions cylindrical and spherical coordinates will help. Alright, so let's however remind ourselves of the 2-dimensional situation, coordinate lines and Cartesian coordinates. Well, here's a Cartesian coordinate system. The coordinate lines are obtained by holding y equals constant, and they are horizontal lines. And they are obtained by holding x equals constant, and that gives us vertical lines. And that means that typically straight objects are very much compatible with Cartesian coordinates, and that's what we know, right? If we now, however, go to polar coordinates, well, the coordinate lines in a regular xy coordinate system are r equals constant, and r equals constant are concentric circles around the origin. And we also have coordinate lines theta equals constant, and theta is a bearing, but which means that theta equals constant. That just gives us rays of the origin, and those are the coordinate lines in polar coordinates, which then certainly tells us that round objects and stuff that just radiates off the origin in one direction, that's something that is very much compatible with polar coordinates. If we are looking at coordinate surfaces, well, let's first look at Cartesian coordinates. Well, if we hold z constant, we get horizontal planes, right? If we hold x constant, we get vertical planes going in this direction. In this direction, because okay, this direction is the x-axis, and so x constant gives us planes that are perpendicular to the x-axis. So we get these coordinate planes, and for y equals constant, okay, now let me get that right. The y-axis goes this way, perpendicular direction is that way. That means that we get coordinate planes going in this direction, and that again shows that even in multidimensional space, Cartesian coordinates are very good for straight objects. We've seen that, for example, in the representation of planes, which have very nice Cartesian equations. Okay, well, if we're looking at coordinate surfaces for cylindrical coordinates, what do we have? We could hold the radius constant, and if we do that, well, remember that was the thing that I said earlier on, I think in the first presentation on 3-dimensional space. When we look at 3-dimensional space, all of a sudden stuff that looked familiar, like r equals constant, reflex, it's a circle. Well, now in cylindrical coordinates, it's a cylinder around the origin, and the cylinders are concentric, right? Because the r gives us the distance of the z-axis, and objects that are a constant distance away from the z-axis are cylinders. Objects made up of points that are a constant distance away from the z-axis are cylinders. Well, then we have the angle theta that we could hold constant, and these angles theta still give us a bearing. It's just that this time we don't get rays, but we get half planes. Because we have a direction, we don't go backwards in that direction, and then we just get half planes here. I've set that up for theta equals 0, theta equals pi over 4, and theta equals pi over 2, 0 degrees, 45 degrees, and 90 degrees. Those would certainly go all the way around, but that was something where it just, it started getting a little bit too busy, so I left that picture alone. And then, of course, coordinate surfaces for z equals constant. Those are easy because those are just horizontal planes, right? You hold z equals constant, you get a horizontal plane. For spherical coordinates, well, for spherical coordinates, we could hold the radius rho constant, and that would give us an object that is made up of points that are a constant distance away from the origin, and that's a sphere. And of course then for different radii we get concentric spheres, which are the coordinate surfaces for spherical coordinates, which means that probably spheres are very nicely represented in spherical, well, spheres are very nicely represented in spherical coordinates because their rho equals constant. Theta equals constant, well, that's the same as for cylindrical coordinates. Theta is a bearing of the x-axis, and so we get these half planes, which are all the points that are lying in that direction of the x-axis. And finally, phi, the polar angle. Well, remember, the polar angle came off the z-axis, and then if I rotate that polar angle around, because I could vary my theta as much as I want, I would get a cone, and that's exactly what I do get. For theta being about 45 degrees, I get this. For smaller theta, I get tighter cones. For larger theta, I would get larger cones, and if theta goes, okay, for theta equals pi over 2, I actually get the xy plane, and for theta being bigger than pi over 2, I would get cones that go in the downward direction. Okay, so we have looked at these two coordinate systems. We've done a little bit of algebra and a little bit of pattern recognition. That shouldn't be too bad. I mean, basically, we just have to remember the conversion formulas. We want to have the pictures in our minds, and then we just have to do the computation, recognizing sine squared plus cosine squared equals 1 every so often. And we also have an idea now of the coordinate surfaces for these coordinate systems. With that, we really don't have much to do. You've got to memorize the formulas, and then we've got some homework problems that make you do the conversions, but this one hopefully will be a fairly relaxing assignment. Okay, I think I'll see you next for limits.